So thank you, Professor Jiang, for your kind introduction. It's my great honor to give you a talk about the thermal structure of the lithosphere. My colleague Yibo Wang just gave a talk about the similar topic about the thermal structure of the continent lithosphere. So here I have make a little bit of difference. I will focus on the thermal and the rheology. As the second is focus on the continental lithosphere instead of the oceanic lithosphere. So let's move. Oh. So the outline will classify to four parts. First of all, I give a briefing background, focus on the relationship between the thermal structure, rheology, and tectonics. And then I focus on the thermal-rheologic structure of the continental lithosphere. We'll focus on the basic characteristics of the thermal structure. Then introduce two case study on how the thermal rheology control the Cenozoic continental deformation. So finally, I will give a summary and perspective on this topic. So as you know, plate tectonics is the great contribution of the geoscience in the past 100 years. So it describes how the Earth works. We can learn a little bit more from the undergraduate textbooks of the geology. So the basic key points of the plate tectonics contributes on three parts. First one, the Earth's surface is composed of the several plates with different areas, such as the Pacific plate, Antarctic plate, and Eurasia plate. So the second one is on Hawley deformation. The deformation just limited to the narrow boundary between the plates, such as the convergent, divergent, and transform boundaries. So little deformation can be found in the interior of the plates. So the third one is about the driving force. So plate motion is basically driven by the mantle convection below, also associated with the ridge push and the slab pulling force. So this is the basic key points of the plate tectonics. So the seminal works were publication in 1916 to 1968. So 10 years before, the UK, United States, and France also give celebrating of the 15 years of the plate tectonics. As we can say, this is from the UK. So in the 2017, this corresponds to the classical paper by McKenzie professor in the natural. So for the United States is hosted by Lamont, so it's focused on the 2016. It's also related to this paper in 1966 about the magnetic anomalies of the Pacific and Antarctic region by Walter Pittman. So for the France side, they hold this ceremony in the 1918. Is focused on the Lepicius paper about the 1968 on the GGR. So this is the basic sketching model to describe how the Earth works. This is the subduction zone. This is the mid-ocean range, and I also can find the transform boundary. So in the after 1980s, so the scientists in the geoscience began to think how to apply this theory to the continental. So to pioneer scientists from the University of the State University of New York and Albany and the Department and the University of Cambridge, two Johns. One is the John Dewey, another one is John Bird. They use this kind of theory to study the continental deformation of the orogenic belts, such as the Appalachian and the Calgary and the Himalaya belts. So, which means the plate tectonics landing on the continent. So another seminal work is proposed by Professor Pittmara and Paul Tablier in the 1975 science. They investigation the Cenozoic tectonics of the Asian continent. As shown in this picture, we can see they use the effect of the continental collision between the Indian continent and Eurasian continent. As we can see, if the India push into the continent of the Asia, can make the rock escaping, such as the Southeast Asia, South China, North China, also associated with the rifting of the basin, such as the Baikal rifting. This is some sediment basin around all this plateau. So this is quite similar work. Till now, the paper has been cited more than 6,800. In 1988, Professor Bitpala also gave a review paper in Nature about the continental tectonics in after the plate tectonics. So he mentioned the two assumptions of the plate tectonics. The first one is the rigidity of the plate, which means the plate is quite rigid, which means there are no deformation within the inter of the plate. Another one is focused on the deformation scale, which according to the plate tectonics, the deformation narrowed to the localized narrow deformation zone. However, it doesn't available for the continent. As we can see, this is the rheological profile of the oceanic lithosphere and that for the continental lithosphere. As we can see, as for the continental, the lithosphere is quite different from that of the oceanic. For the oceanic lithosphere, the strength is increased with the depth, show a large strength, while for the continent, it depends. For example, for the lower crust, the thickness and the strength is quite low, so which means it's some kind of the sandwich, two strong layers intervened with one weak one. So this is not available for the continental. So in the 1980s, with the application of the space geodesy, which make me a more reliable to observe the crust deformation. As we can see this picture, so we can see a lot of the deformation zone is quite larger. It's even wider than 1,000 years. For example, in the Tiansan origin belt is far from the collision zone is about near to 2,000 kilometers. So in addition, this kind of quite a wide plate boundary zone also cover near to the 15% of the Earth's surface, which make me to be serious and think about how the deform of the continent. So I will give a summary about the plate tectonics and the continental tectonics. The first one is focused on the deformation scale. For the plate tectonics, it's originally from the oceanic plate. So it focuses on the interplate deformation. This deformation is quite localized, while for the continental tectonics is focusing on the intracontinental, which means the within the continental deformation. So this is quite different. While for the lithosphere strength, there are also bigger difference. For the oceanic lithosphere, the lithosphere is quite homogeneity and with the large strength, which means it's quite rigid. While for the continent is somehow heterogeneous and with non-rigid, which means the continental lithosphere rheologically is composed of the strong blocks and with weak zones such as the cratons and the riftings and the sediment basins. So this is the totally different in rheological of the lithosphere. So as we can see, the thermal rheological structure of the lithosphere is the key to understanding continental tectonics. So there was another two classical end elements models to describe the continental deformation. The first one is we can call that viscous thin sheet model proposed by Professor Philip England and Don McKenzie professor in 1982. They described the deformation of the continent just like a very thin and large layer. So this is some kind of the numeric model. It focuses on the crust sinking, just like this one, with the indentation of the Indian plate. The crust of the Tibet become sink and sink like this one. So another model is proposed by Professor Paul Tapalia in the same year, which was published in the Journal of Geology. This kind of model can be simplified as the microplate model. That means they use the principle of the plate tectonics to the continental deformation. So we also call it a block escaping, just like this one. This is some kind of physical modeling, which means the analog modeling. So with the indentation of the Indian plate, this plate is quite strong. So which resulting a lot of the large scale stripe slip force around the different blocks. For the first one is the Indo-China block. The second one is the South China, one North China, like this one. So with the condition between the Indo and the Eurasia continents, a lot of small blocks can be escaped from this one. So this is the microplate models. As we can see, they are totally different. So why the continental showed large difference in the deformation style with that of the oceanic plate? I think is the key. The key is that the rheology. So why research the research from the USGS published a paper in the annual review of Earth and Plant Science. So how the continental deformation, we can see a simplified models. So usually with the force from the boundary and also from the interior of the continent, such as the high elevation of the Tibet Plateau. So the rheology would control the deformation style like this one. So as we can see from the plate tectonics, which is some kind of the rigid block, to the continuum model. This is proposed by Professor Philip England on the viscous sheeting model. So we can see from the tectonics to the continuum models. So a lot of transition between them. So it's focused on the block models, just like the Western China. So this is controlled by the rheology of the lithosphere. 20 years before, the National Science Foundation released a white paper on the research strategy on the structure, geology, and the tectonics. So the title is The New Departure in the Structure, Geology, and Tectonics. They proposal, the community of the structure, geology, and tectonics proposal 4 topics for the next 10 years research. The first one is the beyond the plate tectonics, rheology, and organic of the continent, which we can say this is just the topic we are talking. So 10 years later, for the second white paper by the Professor Huntington of the University of Washington, the title is The Challenges and Opportunity for the Research in the Tectonics. They also proposed the grand challenge number 2, understanding variation in the rheology throughout the lithosphere. As we can see, the rheology of the lithosphere is quite important for the continental deformation, while the thermal structure or thermal regime is the key element to control the rheology. So that's why I talk about choose the title as the thermal and the rheology structure of the lithosphere. So at the meantime, for the Chinese community, we also propose a disciplinary strategy report on the plate tectonics and the continental dynamics. So for the scientific challenges, they also mentioned the rheology of the continent and the continent deformation and the intracontinental tectonics. One of the key points is focused on the thermal rheology structure of the continental lithosphere. So in the first part, I will focus on the relationship between the rheology and the tectonics, while the thermal structure is just a linking between each other. So for the next one, I will focus on the thermal rheology structure of the continental lithosphere. So I will introduce what's the basic features of the thermal structure of the continental. First one, I will give a definition of the thermal structure of the lithosphere. This is from the Encyclopedia of Solid Earth Geophysics published in 2020. So by Claude Yapat and Jean-Claude Michel. I'm sorry to know that Michel was passed away in the last year. So in this definition, the thermal structure of the continental lithosphere focuses on the heat transportation process and also about the thickness, temperature, heat flow partition, which means what's the component of the heat flow, how much is from the crust radiogenic contribution, how much is from the mantle contribution, and the temperature distribution with the lithosphere. We focus on the temperature at the Moho zone, and another one is the thickness of the lithosphere. As we know, lithosphere is The thickness of the lithosphere is different with the different definition from the seismology, petrological, and thermally. In geosemics community, we think the thermal lithosphere is determined by the different heat transportation process. In the lithosphere, the heat flow, the thermal transport is the thermal conduction. In the ionosphere, below the lithosphere is the thermal convection. So the boundary between the conductivity and the convective is the thermal is the lithosphere in the geosemics. This picture shows the basic workflow of how we study the thermal structure, rheology, and the tectonics of the continental lithosphere. It's firstly proposed by Professor Sherald Crotty of the Utrecht University in the Netherlands. So firstly, we should know the composition model of the continental lithosphere, which the information can be arrived from the deep seismic profiling and the petrological experience and the rock research. So then we focus on the submodels with the some kind of the 2D or 3D models with the heat flow and the thermal properties as a constraint to make the modeling. So then we can combine the composition information and the thermal structure. We can get the rheology model like this one. We can see the different part of the lithosphere, such as the cluster and up mantle. So for the brown color is the mechanic strong low crust. So after that we can talk about the deformation, which means how the continental deform with the force and the constraint by the rheology of the lithosphere. So this is the basic working flow for the research. So then we transfer to the heat flow partitions. This paper was published in 10 years before by Kevin Furlong and David Champerman. So we can say for the continental and the oceans, the thermal structure is quite different. For example, for the continental, the heat flow is composed of the part one from the crust with the radiogenic contribution of the radioactive elements. Another one is from the mantle, like this one. So for the continental, the heat flow composed of the crust one and the mantle, while for the oceanic lithosphere, it's largely coming from the mantle patch, also with the cooling of the lithosphere. So it's different for the continent and the oceans. In the first 1950s, at the beginning of the geosemic research, the people think there's no difference between the continental and the oceans because there's not too much heat flow data to support. So now we can see they have total different. So another one is about the components of the heat flow. This is the surface heat flow. So this Q crust is the radiogenic heat. So this one is from the mantle heat flow. So the last one is the Q tectonics, which means it's some kind of the thermal effect of the tectonics. But like this one, so for the heat flow variation in the time as shown this plot, so we can see with the increasing of the age, the heat flow began to decrease like this one. So for the part one, like this one. So firstly, the crust heat flow is quite large and then began to keep stable. While for the part three, this is the mantle heat flow is quite stable. Usually for the cratons like the Superior and the East European cratons, the heat flow from the mantle is near to 15 to 20 microwatts per meter square, while for the young genic belts or rifting basins such as the Bohaiwan Basin or the Alpine orogenic belts, the mantle heat flow could be large as the 15 microwatts per meter square. So they are totally different. Besides that, we also should focus on the transient thermal effect like this one, this kind of the extension. So with the cluster extension, we can say this is some kind of the formation of the rifting basin. So first, the heat flow could be a little bit increased because with the extension, the deep mantle can up volume, so which can be produce a little bit more heat below the crust. So the surface heat flow can be increased. Well, with the cooling process of the lithosphere, the heat flow cooling down like this one. So finally, the heat flow is a little bit smaller than the original one. Well, for this kind of the process, such as the contraction process or the condition like this one. So firstly, the heat flow can be a little bit decreased because the two block condition together, the cold crust can be dip into the another one, which reducing the heat flow decrease. After that, the heat flow can increase a little bit gradually because with the thickness of the crust full of the radiogenic elements, so the crust heat flow can be can be from the radiogenic heat like this one. So finally the heat flow is a little bit larger than the original one. So this is some kind of transient thermal effect. Usually we focus on the steady state condition, which means the lithosphere. But if we talk about the really young geological events such as the Indo-Asia collision and also the rifting of the Baikal Basin, we should take into account of the transient thermal effect. So this is the temperature profile of the lithosphere proposed by the Professor Belov. So we can see this is just somehow like that of the oceanic lithosphere, which means the temperature profile like this one. So I will put into consideration about the thermal and the mechanical coincidence. What does it mean? So for the first one, we can say the yellow arrow, which is the mechanically strong crust, which means that this part of the crust is really stronger. So the temperature should be a little bit lower. So the typical temperature range for the magnetically strong crust is about between 215 to 300 degrees Celsius. While for the green one, this is the part of the mantle, so the base of the mechanical mantle, some initial as the MSL. So this one, the temperature is about 700 to 715 degrees. So this is the temperature for the strong part of the lithosphere. Another one is the effective elastic thickness, which means the TE in the lithosphere like this one. So the temperature is about 3 degrees minus plus the 115 degree, which means about 115 to 415. So this is the temperature range for the mechanical lithosphere, which means the strength like this one. So I think it is quite important to combine the thermal and mechanical properties together. So when we calculate the thermal structure of the continental lithosphere, firstly we use the heat flow as the constraint, use the heat transfer equation, numeric or the analytic solution, we can get the profile like this one. So while for the deep part, we can use another geophysical data such as the ping wave. This is some kind of the seismic wave transferred along the upmost mantle with the PN. So this can be give some information about the temperature of the borehole. We have a general common sense. If the temperature is quite higher, the velocity should be a little bit low. So according to this kind of assumption, we can get the information of the temperature of borehole. Besides that, we can use the pressure and temperature data from the zerolis in the mantle parts. This information is usually for the deep part of the lithosphere like this one. So as the Irina professor proposed, she also collected a lot of data in the world like this one. We can see this for the Paleozoic, Cenozoic, and the Mesozoic has different information of the deep Earth. I should be keep in mind that this information by the generalists temperature, pressure data, just recorded the eruption of the magma. So this is the past information of the lithosphere in the thermal aspect. So we use the data from surface heat flow from the magnetic Fourier depth and the PM wave, and also the zeronis data, and also with the seismology information about the reserve function and the topography. So we can integrate for all the kinds of the geophysical and geochemical observation together. We can give a little bit more clear and reliable information of the thermal structure of this continental lithosphere like this one. So let's have some look around this thermal structure of the lithosphere in the large scale as the continent of the global scale. This picture is about the lithosphere thickness for the continental in the Precambrian ages, published by the Arena in 2006. We can see for the old cratons, just like this North American craton, South American craton, and the African craton, also superior, or the East European cratons. The thickness is quite large, about 2050s. Okay, so while for the young genic or rifting belts like this one, this is the condition zone between the Indo-Africa and Eurasia. So the lithosphere is quite thin, about near to the 100 kilometers. So we can see the lithosphere in the thickness is has a bigger difference between the cratons and the genic belts or riftings. So this one is for the deep temperature. This is the depth of the 15 kilometers is near to the crust mantle boundary zone. So we can see also for the old cratons like this North American, the temperature is about 500 degrees. While for the genic belts, the temperature can be high as the 800 degrees, which means the thermal structure, I mean the thickness and the deep temperature should obviously laterally variation for the different blocks and tectonic units like this one. So this is for the I think for the Southeast China, like this one is quite high in the temperature. So let's move to the sedimentary basin. I will take the professor whose work as the case to study. I think Yibo also mentioned this one in his speech. So we can see for the sedimentary basins in China, very interesting trend can be found in the heat flow. For the red one is the red basin with hot basin, which means the heat flow is quite large and larger than the 65 units. Well, for the yellow one is the warm is the intermediate type. Well, for this green is some kind of the cold basin, which means the heat flow is a little bit low as the 50 microvolts of meter square. So from the east to the west, we can see the heat flow for the basins gradually decrease. In the East China, such as the East China Sea Basin, South China Sea Basin, the heat flow is as large as the 17 microvolts per meter square. While for the Northwest China, such as the Tanamo Basin or Jungar Basin, the heat flow is near to 14.5 microwatts per meter. So this is totally different from the east to the west. So this is the thermal structure for the deep information about the thermal state of the lithosphere. They also show the similar pattern from the east to the west. We can got three types. For the first one, you can see, okay, we see the Southeast China. So for this area, for this part, the mantle is quite high in temperature, which means the hot mantle, because the lithosphere thickening, so the crust and the lithosphere is quite thin. So a little bit more mantle materials upwelling in this area, which is reducing the high heat flow and the high temperature in the mantle. So we call it the hot mantle. Actually, the cold crust is just relatively actually compared to that of the mantle. The crust is a little bit cold, but actually the temperature of the cold is also higher. Well, for the southwestern China, the Tibet Plateau, this area, so this is kind of another one. So the crust is quite hot because due to the condition between India and the Asia plate. So the thickness of the crust is doubled as the 17 kilometers. So with a little bit more contribution from radiogenic heat. So the crust is quite hot, while the mantle is a little bit cold. Actually, from the seismic observation, the lithosphere in the Tibet Plateau is about 215 kilometers or 200 kilometers, which also supports the cold mantle in this area. For the northwestern China, this is so I can say this some kind of also for the cold crust and the cold mantle like this one. So it's really interesting if we related the thermal structure to the tectonics or evolution or the elevation of geomorphology of the China. We can say from the western to the east, the elevation become small and small. For the western China, the Tibet Plateau, the average elevation is about 5,000 meters. Actually, the temperature is quite higher. While in the East China, for the East China plain, the elevation is about less than 1,000 meters. Well, so we can say as for the tectonics, for the West China, this is a process between the compression, contraction or contraction like this one. While for the East China, it's some kind of extension. So it is the tectonic process that result in the different thermal regime for the basins in the China. So this is my early work about the Northwest China. We can say the different tectonic units within the North China also show different thermal structure. This is the temperature profile. We can say from the 冯位 graben, 冯位地堑 to the Lucy block, Lucy 地块. We can see a little bit for the 冯位 and Bohaiwan basin, the deep temperature is quite higher. While for the Aldous basin and the Lucy block, the temperature is quite low. So this is the evidence of the literary variation. So how about the rheology? So we can say that for the first characteristic of the rheology of the continental lithosphere is the vertical stratification. As we can see, this is the up crust, this is the low crust, this is the up mantle. We can say for the different part of lithosphere, the rheology, the strength is totally different. While for the oceanic crust, we can say the strength is quite large with the increase of depth. So the rheology of the lithosphere is different between the oceans and the continental. This firstly proposed by the Professor Eugene Beloff. It's so sad to know he was passed away in the 2015. Is quite young. So this is also the case in China. I give you a case study in my early work on the North China Plateau. We can say for this area also show crust extension, such as Bohaiwan basin and the Fengwei Diqian. So with the high temperature in the deep, so which result in the small strength of the lithosphere like this one. While for the Lucy and all the basin, this area suffered with the tectonic contraction, which is compression like this one. So the lithosphere show a large rheological strength like this one. So this is some kind of the rheological Freeman-Britten model. This is the typical sandwich model. This is two also end elements model for the rheology of the continental lithosphere. So how about the European case? This work was finished by the Professor Colletti in the Quaternary Science Review in 2005. So we can also see the rheology show a large obvious later segmentation, which means for different tectonic blocks, they have different rheology for the East European plateau. So the rheology is quite viscous, which means the strong area, while for the laying graben or the alpine organic belt like this one, so it is quite weak. So we can say in the plane view for different tectonic units like the organic belt or the cratons, the rheology is quite different. So we call this phenomenon as the laterally segmentation. So the vertical stratification and the laterally segmentation. So these are the two basic characters for the continental lithosphere. So this is the case in China by Dr. Shen Yujun. We also can from the different color means the different strengths for the China continental areas. For this is the Yangtze areas is quite strong, while for the Tibetan plateau is a little bit weak, while the Tenmo is quite a regional block like this one. So the third character for the rheology of the continental lithosphere is that it evolves with the time, which means the temporal evolution. So for different time scale, the rheology of the continental lithosphere show different behaviors. For very short time scale, such as seismic events, so the lithosphere is quite strong. It's like this one. So it's some kind of the elastic deformation. While for the large, very long-term geological scale like this one, so the lithosphere is somehow behave like the viscous layer, like this one is a plastic or in the viscoelastic. I mean, the rheology of the continental lithosphere is changed with the time. It depends on the time scale. Okay, let's move to the next one. So for the third part, I will give two case study about how thermo-rheological structure control the Cenozoic deformation of the continent. So the first one is about the active deformation and the thermo-rheological heterogeneity, like this one. This is case from China. This is from the Western Canada, like this one. The second case focuses on the thermal weakening of the heat production to the control the intra-deformation. So this is the deep picture of the deep temperature and the thickness of the continental China, like this one. Basically, we can see the thermal structure in the continental China show obvious laterally variation, like this one. So this is the rheological profile of the lithosphere for the typical tectonic zones in China. For the first one is some quite stable area like these cratons. So we can say the rheological is typical sandwich-like. So we also call that weak crust and strong mantle. I have to keep in mind is that it's weak and strong just somehow relatively. Actually, the strength of the crust of the cratons is quite large, but it compared to that of the mantle, it becomes small. So we see the weak crust and strong mantle like this one. This is another end elements like the strong crust and the weak mantle like this one. So this is suitable for the mobile belt like this one. So such as the Bohaiwan Basin or Tianshan organic belt. So between them is the one transitional type like this one. This is available for the Middle China, such as the Ordos Basin or Sichuan Basin like this one. So I also gave a summary about the tectonic domain for the China continent. So like this one, for the stable area, for the transition area and the mobile area, like this one, they have different thermal structure and rheological. We give it a lot of the terms to describe, such as the heat flow, motor temperature, thermal lithosphere thickness, the total strength, and the elastic effective elastic thickness for the lithosphere. We can see they have different in the numbers. So also give the case for them like this one. So let's move to the earthquake pattern in China. As we can see, a lot of earthquake between the eastern North China, while for the western North China is quite stable, because as we showed before, we can see the rheological structure of the lithosphere between the western and eastern North China is totally different. So for the eastern one, due to the Pacific of the subduction of the Pacific plate, which result in the destruction of the North China craton, so which result in the quite weak of this area with a lot of the magmatism and the mineralization and earthquake like this one. So while for the South China is quite stable, so just a lot of earthquake available around the coast area like this one. This is the Hainan Island, this is the Guangzhou. So while for the West China, we can see between the Tainan and the Jingao Basin, this is the Tianshan organic belt, a lot of earthquake. As we showed before, the neurology and the neurological strength of this area is quite weak compared to that of the stable cracks. So with the force from the India-Eurasian collision, so this area is probable to deform with the earthquake and earthquakes. So this is the active tectonics classification of China proposed by Professor Deng Qidong. So we can see a lot of blocks with different areas in China. This is the South China blocks. This is the North block, the Northeast blocks, and this is the Northwest blocks. We can see a little bit similar to that of the distribution of the earthquake like this one. So I think this basic pattern of the classification of the tectonic area it's controlled by the rheological and the thermal state of the lithosphere. So another case, and this is also observed by the GPS observation, which can see the GPS velocity like this one. We can see for the Tibetan, for the Canadian frontier, which this one is a high strain, which means the deformation is quite intensive. So for this is the Northeast China, this is the South China. You can see without any little deformation within this stable blocks. While for the Tibet plateau, a lot of deformation like this one. So it also evident for the rheological distribution in the lithosphere. So the second case from the Western Canada, like this one. So this is the general tectonics for this area. We can see with the subduction of the Wand-Fokker plate into the North American, a lot of volcanoes and earthquakes along the Western Canadian. This is the Cascadia mountain range, like this one, a lot of earthquakes. So while for the inland of the Canadian, so there's a lot of earthquakes. So why? This is the deep sum structure proposed by the Roy Hayden professor in the Canada Geological Survey. So as we can see, for the western coast area, like this one, this is a Cordillera area, is quite higher temperature. It's more than 1200 degrees Celsius, while for the craton like this one, so temperature is about 800. So this is the thermal profile, temperature profile combined with the Moho from the PM wave constraint, also with the generalist PT data. So this is a totally integrative profile for the deep temperature variation for this area. We can see for the Cordillera and the craton, they have different thermal structure. This is the rheology and strength for the Western Canada, like this one. So for the Cordillera area, the elastic thickness is about 20 kilometers, while for the craton is about 100. It's totally different. While this is the rheologic profile like this one, this is the rheological profile for the organic belt. This is for the cratons. We can see the strength is quite different. This is very large for the craton, while it's quite small for the organic belt. So Heinem also gave the deformation scale for this area. We can see from the subduction zone to the back arc to the inland. So they have different deformation scale. So in the collection zone, it corrected by the cluster sinking like this one, while for the back arc is extension. While for the this is the frontier mountains. The crust is a little bit sinking, while for the craton is keep stable. So this is a different deformation style from the subduction zone to the big arc area to the inland continent, the cratons. So this is the modeled strain between different areas like this one. So this picture of the deformation is controlled by the rheological contrast between the different areas. This is the big arc with the low rheology, while for the craton is high strength. So Roy also give a summary about this kind of tectonics and the deformation, which means the subduction zone, big arc, mobile zone, and the orogenic heat. So the key point is that the big arc areas is inherited by the previous organic weight, which can be shown a little bit of high temperature and a large heat flow. So it's rheologically weak. So with the force, with the subduction and the tectonic force, this area, the big arc can be a little bit easy to deformation. So this is the relation between the heat flow, thermal structure, and rheology and the tectonics. So another case is about the intracontinental deformation with the thermal weakening. This case from the Australia, as we can see, so for the southeast southern Australian continental margins, so for this area, the heat flow is quite higher. It's really interesting that earthquake is also frequent. So because for this area, this is a granite area with the large heat production is a little bit about higher as 10 units, while for that of the area, the heat production is about 1 or 2 units. So this big contrasting between the heat production, which results in the difference in the surface heat flow between the this area and this area. So we also result in the seismic pattern in this area. So this is another case from the North European case by Professor Clinton and Van Vins in the geology in the 20 years before. So they talk about the tectonic basin inversion and intraplate deformation in the North European. They think this is also due to the changes in the strength of the lithosphere. They call the strength reversal. So why the strength of the lithosphere can be changed just due to the magmatism and also the neotectonics. So this we can see from the 250 million years before to present, the lithosphere became weak and weak, which result in the basin inversion and a lot of earthquakes in this area. In the last picture, I will give a brief summary. This paper published in the Nature Geoscience in 12 years before by the Mountain 3. So they gave 2 conception models with the continental deformation and the thermal rheology. For this one, this is some kind of the really weak lithosphere, which means the high temperature in the more and the small strength for the crust. For this one, we can see the effective elastic thickness of the lithosphere is 25 kilometers. So for the deformation, it's kind of the thick scaled belt, which means the deformation, the crust shortening is quite large, and also with the involve or the basement for this one. While for the another case is from the craton area, so the effective elastic thickness is about 17, is quite larger, so which means the lithosphere is quite strong. So for the surface deformation, it's a thin scaled belt, which means the deformation and the crust shortening focus on the upper crust like this one. So we can see the crust shortening is about 35 to 70 like this one. Well, for this kind of one, the basement, the deep part of the crust can also be involved for the deformation. So this is for the thin scaled deformation. This is for the thick scaled deformation. So why they show different behavior? Because they have different lithosphere. For that one is a weak lithosphere mantle, while for this one is a strong lithosphere mantle. So this is a good case to show how the rheology and the thermal structure to control the surface deformation, or mean the intraplate or mean the Cenozoic deformation in the Earth. So for the future works, the first one we should focus on the basic data acquisition. I mean, although the heat flow data increased rapidly during the past 16 years, but it's not enough to investigation of the thermal structure and deformation. So we also need a little bit more heat flow measurement, and also with the deep seismic exploration in the lithosphere. So for the third one, we should focus on some rock physics experience with the high temperature and high pressure condition, which can give more information about the rheological parameters of the typical rocks within the lithosphere. For example, for the upmantle rocks, paradites like this one. So another is also later further research is the composition. We should be know more about information about the composition. What's the main rocks of the deep earth like this one. So finally, I think it should be in combine all the information from the heat flow, seismology, and the rock physics into the geodynamics modeling. We can give a more story about how the continent deforms with the rheological deformation. I think this is the urgent task for the future for the thermal structure and the tectonics in the continental lithosphere. So I think I to stop here. Have any questions?